like to thank Pascal Lee for giving me the possibility to talk about this topic. Yeah, can you hear me now? Great, great. Okay, so yeah, I'm actually a NASA postdoc here at NASA Ames, and I would like to thank all the co-authors about the work we have done here. So what I'm going to show you today is the distribution of the Phobos groups on the surface of the object and the stereographic perspective. Okay. So regarding the origin of Phobos, we have heard about it yesterday, and there are many questions about its possible origin, and it's still debated. It can be formed from a disk of debris, whether as a remnant of the formation of Mars or as the result, possibly, of a collision between Mars and a large body. And the second possibility that we have in mind is that it's an asteroid that was captured. Indeed, spectral observations that were taken in more than 40 years, they show that there are physical properties that are similar to D-type or C-type asteroids. But then it's the origin of Phobos is not the only thing that is harshly debated between the scientific community. Even the grooves distribution and the grooves analysis is something that is pretty tricky. And as you can see on these images right here, these are almost all HRSC images. Grooves are almost everywhere. They are located on the southern hemisphere of Phobos, the northern hemisphere, and they cross all along the equatorial region. There are just few specific areas where there are not a lot of grooves, but otherwise they are almost everywhere. So grooves, they are not really a feature. I mean, they are a feature that is common on different asteroids that were observed in high resolution. For example, right here, you see that there are equatorial grooves on the surface of asteroid Vesta observed by dawn. Then there are also grooves present on the asteroid observed by the Rosetta spacecraft 21 Lutetia in 2010. They are almost everywhere, and they are basically related to the impacts on the surface. And then there are also grooves on the asteroids Eros that was observed by the Near-Shoemaker spacecraft. But these are just three examples. There are grooves observed also on Gaspra and, for example, on Ida. So talking about the Phobos debated grooves, they were first observed in the Viking images. And since then, their origin was greatly debated because unless the other asteroids, Phobos, of course, it's orbiting Mars. So it's a kind of different situation with respect to the main belt asteroids or near-Earth asteroids. So the Phobos orbit is actually around Mars, of course, and it's well inside the Roche limit. And there is also the presence of an important feature, which is the Stickney crater, which is a 9-kilometer crater on the surface. So the possible origins of the Phobos grooves, they have been attributed to whether the tidal stress on a homogeneous body around Mars, then possibly dynamic loading due to the impact rate creating the 9-kilometer Stickney crater, then possibly related to secondary impacts due to the Stickney crater, or secondary impacts resulting from primary impacts happen on Mars. So in 2014, there was this important work published by Murray and Heggie, and it was presenting a summary of maps. And right here, you see the possible origins of the grooves and their distribution, what kind of distribution we are expecting on the surface. In this specific case right here, in the work of Thomas in 1998, these are the grooves that we expect if we have Stickney ejecta boulders, if we have tidal stress on an homogeneous body, a work done by Dobrowski's in 1982, then Stickney rolling boulders, and then also Stickney fracturing. And then in this work right here, Murray is a great supporter of the secondary impacts from Mars, and then the ejecta that are just lifted up, and then there is Phobos taking them. And this is the map of Phobos grooves, and this is the secondary impacts from Mars as the map that was shown by Murray in 1994. So these kind of maps, as you can see, they show that, first of all, the tidal stress alone, it's really difficult to be used in order to explain the observed groove distribution. And then there is also the problem that there is an uncoeval origin of the grooves, and there are several systems that are younger than the Stickney crater. So it's tough to say that they are depending on the Stickney placement. On top of that, even if we have this kind of distribution, which is kind of similar right here, but then there was this work of Ramsley et al. In 2014 that was concluding that the volume of ejecta coming from Mars, they're not enough to produce, and they are insufficient to produce all the grooves of secondary craters that we see on the surface. So despite the fact that Stickney was ruled out, and then we're going to show also another evidence that was ruled out as the main cause of much of the grooves on the surface, there is still the possibility that there are other grooves that they are representative of fracture and joint planes related to other craters on the surface of Phobos. So in this kind of work that I'm showing, we are investigating the hypothesis that the grooves can be expression of fracture planes, and then we try to derive their spatial distribution on the 3D spatial distribution and reconstruction on the 3D models. Okay, what do we use here? We use stereoplots and cyclographs. They are stereographic projections, and what I'm gonna show you here and what I'm stressing here is that this kind of analysis, stereoplots and cyclographs, they are used to consider the orientation of a set of planes, the planes that we are considering the fracture planes. So we are not really considering their relative spatial distribution, but how they are oriented with respect to one feature or another on the surface of the asteroid. So here we have a reference plane, here we have a fracture plane, and once we have a vector right here, that's the perpendicular one, and the intersection with this one with a sphere here, we define a vector which is called pi, pi, and then we also have the set of lines that are here, and this is called the cyclograph. This is considered the curve that's the C1 right here, and this is the projection that we see looking north. So the projection of pi, the pi and ci, the set of pi first is called stereoplot, and the set of ci first is called cyclographic projection. In addition, the point P1 right here, Pi right here, can be representing using two angles, like the deep angle alpha and the deep direction delta of Pi. That's other ways to have the orientation of this distribution. So once we talk about this, we have to take into account what kind of reference system we are using. Here we have a sphere or Phobos, or what kind of object you are interested. And here you got like the rim of the crater, or a specific rim of a surface of a target that we are considering. And these kind of fractures right here, in this way, you see they are always perpendicular to this plane, all along the body. And once we use this kind of reference system centered on the crater, we call it relative, and all the grooves that are radial, here we have the North Pole, the South Pole, the West, and the East, and all grooves that are between -20 and +20 degrees, so in this direction, inside this cross right here and this cross right here, they are related and they are radial to this specific feature. In the case of the absolute reference system, here we are just looking north, so basically we are looking in this direction, in this case, right here, and this is the North Pole, let's say, of the feature that we are considering, and all the possible planes, in this case, these that are parallel to this, they are on specific location, but their orientation is, the vector of their orientation is looking north or south, and they are all clustered around around 20 degrees far from the north here. So what did we do? We identified 352 grooves on the surface of Phobos, and then we were deriving the spatial distribution. Here, I'm just underlining 3 of the main craters that we see on the surface, and then you can also see on the 3D shape model. I brought it, we printed it at the University of Padua. And this is the Stickney crater, this is the Gulliver crater, Flimnap crater, and then there is an area that we call Occultus, where it's one of the area where there are not a lot of grooves, but there are a lot of grooves that are radial to this specific area. So regarding the Stickney crater and doing the analysis that I was showing you, we have 5.1% of grooves that are radial, while around 1% that are parallel. Then regarding the Gulliver crater, we got 3.1% that are radial and 9.5 parallel. And looking at the Flimnap crater, the third one that we were analyzing, we have a 1.7 that are radial and 7.7 that are parallel. Then there is this region that we call the Occultus. It's a positive feature right here. And in this case, we have a 6.5% of radial grooves, while we don't really have any parallel grooves. So of the 352 grooves that we have identified, only 27.6 they are associated with main craters, so they have an origin related, the possible origin related to the main craters. And of these, just 10% of all grooves, they are radial to these features. Since other formation scenarios, like for example grooves due to chains of secondary impacts, or grooves resulting from Mars tidal stress, they cannot explain the observed distribution, we need to consider a different origin. So at that time, we were considering that in the paper that we have published in 2015, Bukowski et al. In 2008 was showing that some of the Eros lineaments, they are not really related to specific impact craters, and they were suggesting that these kind of grooves that we observe on the surface of Eros, they can be derived as a fracture. They are the result of emplacement on craters on a previous asteroid, and then Eros is just a shard that inherited these scars. So the first thing that we were suggesting in 2015 was, is it possible that Phobos grooves are also the results of this kind of analysis? This was just as a first step that we were doing. But what about if we do a stereographic continuum analysis? So what I was showing you is the analysis of specific craters on the surface, so let's call it discrete analysis. What about a continuum one? So we pursued the stereographic local analysis, and we were just trying to use each kind of facet on the surface of the 3D shape model of Phobos, trying to understand for each facet what is the possible percentage map of radiality. So where these grooves are really originating from the surface. So not just focusing on one crater, but on the surface, and then give it a try on the surface and trying to understand what is the percentage. And here we found out that there are two specific regions. One is centered at the apex of Phobos, and it has a maximum value of 23% of all grooves. They are just radial to this area, close to Stickney, but on the apex of Phobos. And the second one is centered on the antapex of Phobos. So as a conclusion here, we have the two areas where the radial grooves are more abundant, and they're not really related to major impact craters. We don't really see anything here, not even here. This is the occultus region. This is the region close to Stickney. And in 2015, Aspo et al., they calculated the stress field map derived from 10% of Phobos orbital decay. And they were deriving tension stresses and compression stresses on the surface. And the tension stresses here, they are presented here with a black line, and the compressions in the gray one. They are radial to the tidal bulge. While the compression stresses, they are concentric to the tidal bulge, and they are radial to the two identified areas where they seems to originate. So this seems to support the suggestion that Phobos grooves are the results of a possible tidal deformation due to the possible deorbiting to Mars. Thanks.
The floor is open for questions.
Jim Head, Brown University. Yeah. Really nice treatment. But before you rule out radial textures as non-radial textures as not coming from Stickney, there is a lot of suborbital ejecta that comes back down in and produces crater chains and other things not radial. So that's just something to keep in mind in terms of the overall analysis. And we have a poster again, an unabashed advertisement number 4 that treats some of this stuff. Okay.
And you're talking about the craters that you really see close to Stickney, like the line, yeah.
There are no other questions. Thank you, the speaker again. And for the next speaker, Terry Harford, tidal activity on Phobos.